prova. Ok.
Bene, buon pomeriggio a tutte e a tutti. E oggi per me, per voi, per tutti è il grande giorno, quindi è l'evento di chiusura delle 3 settimane di WebValley. Per me è sempre una grande emozione avervi tutti qui, avere gli studenti, i tutor, gli ospiti, i ragazzi, i parenti, i docenti, insomma tutti quanti. È una bella festa perché credo che avete tutti lavorato duramente per 3 settimane e oggi siamo qui a presentare anche i risultati che, del vostro lavoro. Abbiamo avuto 19 studenti, studentesse da diverse parti d'Italia, del mondo, con diverse culture, diverse origini. Avete lavorato bene insieme, è stato un piacere vedere il team quest'anno. Abbiamo avuto 4 studenti del Trentino Alto Adige, 7 regioni italiane, Veneto, Puglia, Sicilia, Abruzzo, Molise e Emilia Romagna e 6 studenti internazionali, 4 dagli Stati Uniti, una studentessa dal Brasile e una dall'Arabia Saudita. La tematica proposta quest'anno è, direi come sempre, però è bello avere anche queste tematiche su cui ragionare e analizzare i dati, aveva e ha un grande valore scientifico e la squadra dei tutor per me è stata davvero eccezionale. Ho avuto l'onore e il piacere di lavorare con i colleghi dell'unità di Data Science for Industry and Physics. Ringrazio Marco Cristoforetti di aver messo tutto il suo team a disposizione, o gran parte di esso, i ricercatori e le ricercatrici di Italia Meteo, che sono anche stati con noi durante le 3 settimane, anche i colleghi di Meteo Trentino, AI Factory, l'Università di Trento, Meteo Network, Appa Trento e Cineca. Quest'anno Gabriele Frank è stato responsabile scientifico dell'edizione del 25 insieme a Elena Tomasi. Perché vi racconto questo? Perché Gabriele è stato il nostro studente WebValley 2002 e ha fatto poi il bachelor, ha fatto il master con noi, il dottorato e adesso sta concludendo la sua tenure, quindi è per me un piacere aver avuto tutta questa, questo percorso affiancato a Gabriele. Non è l'unico studente di WebValley, abbiamo Luca Coviello, edizione 2012, ci accompagna come tutor ormai da diversi anni e per me è risorsa fondamentale di WebValley, quindi io non finirò mai di ringraziarti dell'impegno e della passione che dedicate sempre ai ragazzi e alle ragazze di WebValley. E quest'anno abbiamo anche una new entry, avevamo Tommaso Osemer che ha fatto WebValley con noi nel 2023, ci ha accompagnato, ci ha aiutato col sito, con le application, quindi insomma, che dire, grazie a tutti. Io do il benvenuto anche al comitato scientifico, sono colleghi, sono amici, quindi li coinvolgeremo soprattutto nella discussione alla fine della presentazione dei ragazzi. Abbiamo Andrea Piazza del Servizio Prevenzioni e Rischi della Provincia Autonoma di Trento, grazie Andrea, Martina Calovi, professoressa associata della Norwegian University of Science Technology, grazie Martina, e Roberto Visintainer, Senior Researcher del COSBI, quindi grazie davvero di essere qui con noi, aver accettato, chiamiamolo invito, però insomma è importante per noi avere anche questo momento di confronto con i ragazzi. Ultima cosa, io ricordo che WebValley ormai dal 2020 è in collaborazione organizzata e condotta con l'Istituto Artigianelli di Trento e quest'anno quindi vorrei fare una cosa speciale, quindi per me è bello avervi qui per condividere questo ed è il lancio del manifesto di WebValley. E per farlo qui vicino a me c'è Giuseppe Jurman che condivide questa avventura, ormai sono più di 15 anni che facciamo WebValley insieme e invito qui con me Eric Gadotti, dirigente dell'Istituto Artigianelli e i colleghi coinvolti Nicola Gadler, Denise Fox e Virginia Spallino. Grazie mille.
So let's switch to English, and thanks a lot for being here to everybody. It's the 25th edition of WebValley, and it's a real pleasure to have you all here for this final presentation of the FBK Interdisciplinary School for Data Science and AI. Since 2001, we had almost 500 students that has walked this path of the 3 weeks of WebValley. Started out as a very local and regional initiative for high school students, 17 to 18 years old, has grown up in a larger event involving international students now. And I mean, it's been a long trip since 2001 now. And we want to stress out that since we started this partnership with Istituto Artigianelli, WebValley has risen in something quite different. It's been endowed with a comprehensive experience fostered by a broad educational community, including dedicated teachers, scientists, and experts in innovation, new pedagogical approaches, and inclusive education. And as Claudia has anticipated, we want to use this moment to launch this new initiative, which is the WebValley Manifesto of Excellence. And in the next 5 minutes, we will present what are the pillars of this Manifesto of Excellence. And the first one is indeed the research, the applied research. Okay. Every year, WebValley proposed to the students some scientific challenge which is not explicitly tailored for the school, but is carried out from a real project, a real research project of the institution, of the research unit that is proposing the edition. Okay. What are the things that are, I mean, identified, characterizing WebValley as an experience? Each participant is treated as a colleague, from junior student to researcher, and the choice of themes that are indeed ethically relevant, okay, has demonstrated that AI application can activate the potential of students of all gender and different personal stories. What is the structure with WebValley? We are dealing with 3 weeks of research, and in the first week we are providing all the scientific, technological, and let's say computer science tools that will be needed to deal with the challenges we'll propose during the second and third week. In these second and third weeks, the participant should demonstrate their ability and all their potential to solve the scientific problem that the researchers are proposing, and that later will be very helpful to the researchers themselves to carry out the research in the specific project we are using. And during all this trip, I mean, clearly the research, the student benefit not only for the help from FBK research, but also for the researcher of international institution and junior technologists, and other WebValley alumni that can help and support, okay, their work. And this is the presentation of what ended up for this year. And with this, I leave the stage to Professor Gadotti, and thank you.
Okay, thank you very much. Good afternoon, everyone. This is, for me and for all the persons of our community, a very important moment because Artigianelli and FBK want to spread publicly a thought that we have in our hearts and that has characterized all our work in these years. Artigianelli is now an ecosystem made up of a school, research institutions, and companies that work together to help each student to find their own path in the life by experiencing success. Each student within this educational reality can build their own path to become what they are excellent. We believe together that the innovation of a civil society can only come from the valorization of all differences. When a society is able to take the best of each person and valorize it for the good of all, then it is a healthy society that will grow. When I speak of valorizing each person, I mean real everyone. In particular, people characterized by neurodivergencies, by the way of thinking different from the common, or who have pathologies, or who have, for example, different ages, and so on. It is only by putting together different people to solve problems that innovations are born, and we do it with our students using design methodologies. WebValley is a small but important example of this model. In WebValley, many students, very different in age, school, ways of thinking, or who have different different type of think or speak and so on, have put together the skill to develop something great for everyone. Thanks to all the people who believed and believe in it. Thank you very much.
All right. Hi, everyone. I'm Nicola from Artisanelli, and I'm part of the WebValley tutor team. So for over 2 decades now, WebValley has been a benchmark for scientific excellences. But today I'm here and I'm happy to share excellence beyond the lab, so what we have heard so far, transforming how we communicate our identity and share our journey. We've established a unified visual identity for WebValley, so our signature of quality made visible in everything, from the Quaderno of WebValley, which we presented formally last year, to our professional poster and the social media covers that we've been through in these 3 weeks.
Pronto?
Okay. So more profoundly, we've implemented a new hands-on process for telling our story through a series of workshops, for example, design thinking, the business model U, or slide design, public speaking, everything related to PR, social, and communication in general. So with this, we empower our students to become the primary storytellers of the story, to refine their narrative through continuous group feedback, which we've been going through these past 3 weeks, and mock presentation, which we've been doing a lot in the past couple of days especially, and also taking true ownership of their work for the students. What we'll see in this final presentation that is going to go on in a little bit is the culmination of this entire journey, a story not told for our students but by them. This is the new standard of excellence for WebValley skills outreach in general, and we hope it's going to empower the next generation of scientific storytellers, so our students here today. With this, I would like Denise to go on with from now. Thank you.
So basically, as Eric and Giuseppe and Claudia was saying before, WebValley takes place at Artisanelli Institute, where basically our design thinking approach shapes not only the way we work, but also the way we design spaces. And we create environments that support and develop collaboration, creativity, and teamwork. Students don't just study and learn like passively, but they experiment, they share ideas, and they solve real problems through creative collaboration. So, for example, in this slide, you can see some of the places we have been living and working in through these 3 weeks together with all the students and all the tutors as well. But it's not all about work, right? So basically, outside the labs, we have green spaces, common areas where students can relax, talk, and basically connect with each other. These informal moments are just as important, and we include mindfulness sessions, soft skills workshops, team building activities that bring everyone together and facilitate interactions. Because basically we believe that learning happens not only through content, but also through relationships and shared experiences. Now, my colleague Virginia will talk about the inclusivity and well-being model in Artigianelli. Thank you.
Okay. The last part of this presentation of the manifesto of WebValley, if you look at the slides, instead I'm speaking, you can imagine the project. Personal well-being is the foundation of learning and growth. A central place in Artigianelli is Art Café. Art Café is a lab, a project managed in collaboration with Reactiva, a social cooperative which brings a larger perspective on social inclusion in line with the mission to supporting work integration for disadvantaged people. Smart cooking reinforces this idea. It's a project which involves not only psychology and educators for the observation and promotion of positive social and relational dynamics, but also students for Artigianelli School. These students take part in the workshop as an opportunity to change themselves and to experiment collaboration, responsibility, emotional regulation, and other soft skills essential to their educational and personal development. The interaction among various people, like students, like trainees, like social worker and psychology, creates a rich and different setting where every daily action becomes an educational opportunity and a shared experience of well-being. This is Artigianelli. Artigianelli is an ecosystem that brings together excellence from various fields to promote individual well-being. Thank you so much.
So now let's move on to this year edition of WebValley. As you can see, the title this year, the theme was Weather Meets Artificial Intelligence, Building Tomorrow's Earth Science. So this is basically what we try to do with my group at FBK every day, and we wanted to share this passion with all the students this year. We had a great opportunity to share this journey with important scientific partners. Meteo Trentino, who is here in the audience and will be in the scientific panel, Meteo Network, and especially Italia Meteo. We do have connected with us, here they are, two of the tutors who joined us during this week, Francesca Vittorioso and Daniel Pavone. They worked with the students side by side during these weeks, and we are really lucky today to have with us also the director of Agenzia Italia Meteo, which is the meteorology and climatology Italian agency. So if Carlo, would you like to give your greetings? Thank you.
Okay. Thank you, and good afternoon, first of all, and thank you for this opportunity that you have given to me to give a brief greeting to all of you and to the organizer, whom I congratulate for the excellent organization of this WebValley 2025. And where you have discussed, as you mentioned before, and as I read from the title, the theme, the topics of weather that meets artificial intelligence to build the earth science of tomorrow. That is really a very, very good sentence, because this is a real revolution for the science of meteorology in particular, but in general for environmental science, the use of artificial intelligence. Of course, the interest of Italia Meteo Agency is very large for that. The weather forecasting using artificial intelligence is really a new revolution. I can say it is a sort of a Copernican revolution, probably, because the use of machine learning for the weather forecasting at the different time scales is really very, very important. And for me, that I am quite old, it was not thinkable until just a few years ago that it could be possible to make good weather forecast using at the best the data. So these new technologies is really impressive and important because allow us to use a very huge amount of data that is already available. And so I am sure that the different challenges that you have explored with the student and the student have created are for sure very, very interesting, and I will here to see these results, and allow me to thank all you, and also a special word also for my colleague Francesca Vittorioso and Daniel Pavone, that I know that have collaborated with you for the good behavior of this course. So thank you again, and of course Italiametro is ready to open the door for students who are interested in visit our institutions and to explore if there are other possible possibilities for working in the future. So thank you again, and I will hope to collaborate with your institution much more in the future. Thank you very much again.
Thank you very much, Carlo, again, and Francesca and Daniel. So I think that's the moment of the students. So let's really hear the story from who lived this year experience. Thank you.
Hello, everybody. My name is Ethan Kim. I'm from the United States of America, and I'm pleased to introduce to you what we've worked so hard over the last 3 weeks. But first, what is WebValley? WebValley is an international summer program located in Trento, and it brings together students from all around the world. At WebValley, we immerse ourselves in a true interdisciplinary research environment. We collaborate to tackle real-world challenges using data science and AI-based technology. We are a team of 19 passionate students collaborating with researchers from many different backgrounds, but our shared commitment unites us and drives us to push the boundaries of scientific discovery. When WebValley started back in 2001, it began as a small initiative aimed at empowering the local youth with innovative technology skills. Fast forward to today, it proudly hosts Italian and international students from all these countries over the years. But now I have a question for you. We all come from different backgrounds, but what is one experience every human shares? Well, the answer is weather. We've all experienced weather, right? Weather is one of the most impactful things to the human experience. Since the ancient Sumerians, weather has been a big deal. Back then, weather could control when your harvest was, whether you ate or not. Obviously, things have certainly calmed down since then, but it still affects us to this day. Although we cannot change the weather, being knowledgeable of what you expect is still very important. Weather affects how humans go about their day, whether you bring an umbrella or you wear short clothing, because it's hot outside right now. But, everyone's checked the weather before. But in seriousness, forecasting is very important. For example, farmers rely on knowing how much precipitation they should expect for the next few weeks. Even concerned scientists track the weather to observe climate change. It is no overstatement to claim that weather is a big deal. Everyone relies on the weather forecast, and recently machine learning has been becoming more prominent into the forecasting process to provide more accurate predictions. Machine learning is revolutionizing how we analyze and predict weather patterns. Traditional forecasting methods rely heavily on physical models and historical data. But machine learning adds a new dimension by uncovering complex patterns and relationships that the human might otherwise unnotice. As you can see, the numerical weather forecasting for 3 days has reached nearly 100% accuracy over the years. It's only a matter of time we can accurately predict weeks in advance. Though through the decades, the improvements in skill of weather forecasting has increased. And we gained about 1 day of predictability over each decade. This revolution has been recently propelled by the advancement of machine learning. So we broke our main goal of WebValley down to 3 parts. We broke it down to missing data reconstruction, quantitative precipitation estimation, and subseasonal forecasting. And we will present to you the results which we were able to achieve in just these 3 weeks of this WebValley program. And I would like to now pass it over to Anita of Challenge 1. Oh, yeah.
Hello, everybody. My team and I have worked on reconstructing missing data in the Meteo Trentino weather station records. According to the World Meteorological Organization, missing or incomplete weather data is a widespread issue that can seriously reduce the accuracy of forecast and climate models, with real consequences for public safety and environmental planning. So, without data, there is no forecast. Why is it important? Well, many working fields depend on weather forecasts. So, this issue is particularly relevant in meteorology because by filling the gaps in historical datasets, we enhance data quality, which leads to more accurate weather forecasts and a better foundation for studying climate change. So, what is our focus? What have we worked on? Well, the location where we are working is the Trentino region. In Trentino, weather information is handled by Meteo Trentino, the provincial weather service that manages a 171 station network. They have been maintaining this data diligently for over 100 years. It is thanks to them that we now have detailed regional data to work on today. This data is high quality, but as is often the case with technology, things don't always go smoothly. Weather stations can malfunction due to aging equipment, dead batteries, or even simple transmissions error. These malfunctions cause data gaps. These gaps can bias climate statistics and reduce the reliability of our models. Previous research has shown that filling these gaps is crucial for maintaining data integrity and improving forecasts. So, our goal is to identify these gaps and fill them in as accurately as possible. And now, I'm going to hand it over to Ethan.
Nearly 13 million of the total 294 million data values from these stations are missing, which adds up to about 4.43% of the data. These are the values that make up the gaps in this data set. Even though 4.43% may seem small, this amount of data can be years, even decades of unusable data. Our goal is to reconstruct each data value, but obviously we can't do that by hand, so how do we tackle it? Well, our goal was to reconstruct these missing data from this data set, and to get there, we first identified the gaps and anomalies in the data of the Meteo Trentino data set. We did this by using visualization, algorithms, and quality indexes classified by meteorologists. After that, we created artificial gaps so that we know the real result should be as compared to the predicted result from our model. And we trained a deep learning model that can fill in these gaps. You might ask, why are we using deep learning? Well, from our prior literature review, it showed that deep learning was a very promising solution to the issue of data reconstruction. Deep learning is the state-of-the-art method for gap filling with its neural networks to improve its accuracy in reconstruction of data. Now I'd like to pass it off to Michele, who will talk about our data sets.
We are using 2 different data sets. The first one is Meteo Trentino since 1920, but we are using data since 1985 because from 1985 on, Meteo Trentino uses automated data measurements with over 9,000 cumulative years of weather measurements. And then, as a second datasets, we are using ERA 5 land area analysis, ECMWF global datasets, available since 1950. But let's go deeper in this. We are using 171 different stations that can measure different variables each, all located in the Trentino regions. All these values are points in a time series, and one of the main challenges that we encountered while working with these datasets was heterogeneous temporal resolution. Values are recorded at varying intervals, so in order to improve our datasets, we had to create some procedures to align Meteo Trentino and ERA5 datasets. Data 5 is a comprehensive long-term dataset of past weather and climate condition. In other words, area analysis. It has hourly resolution and provides us gridded estimates of a huge range of variables, such as atmospheric, land surface, and ocean wave parameters, but we just use land surface parameters. We use it to train the model to fill the gaps in the Meteo Trentino series. However, while ERA5 offers excellent consistency at the global scales, it lacks of precision on a local scale due to the fact that its native resolution is 9 kilometers. For this reason, it was necessary to align ERA5 and Meteo Trentino stations in order to ensure compatibility and reliability on the modeling process. These that you can see are some of the variables that are contained in our datasets: temperature, humidity, and pressure. All these variables are related, as you can see from the graph, which is a plot of a temperature over a certain time period. They have a pattern depending on the time of the day and the seasonality, and we choose to focus on temperature. Then there is these other variables: wind speed, wind direction, and precipitation. These variables, as also is shown with the graph, don't have a pattern, so it's harder to work with them, and we choose to focus on the wind speed. Of course, the model can also be used to work with other variables with some works on the data, and now I'll pass the word to Daniele to show what we did with the data.
So, in order to get to the model, we had to first analyze the data and work on it by using the two datasets' complementary strengths to achieve the best input possible. So, first, we had to filter the data by using one of the features that the Meteo Trentino data has, which is the quality code. The quality code is a value given by an expert meteorologist that checks some of the Meteo Trentino data and describes basically the quality of the data. So as we can see in the graph, we have this clear separation between the red part, which are the raw, non-validated data, and the blue part, which will also be the input of our model, which is the checked data by the expert. And then we had to interpolate the ERA5 data with our good data. So, since ERA5 has a lower frequency than the Meteo Trentino stations, we had to multiply for every hour the data of ERA5. So, as we can see in this graph, as shown by the arrows, we have some clear steps that sign that we have the same value for an hour. We had to multiply it because our model needs to have the same number of values for both data sets because it has to have a fixed number. And then now we can create the artificial gaps that we need to reconstruct for the training part. These are very important because then we can create a controlled experimental setting where we can create when we can recreate real-world missing data, so we can try and train our model. Then the data gets split into three parts. The first 70% goes to the training part, so about 186 million of lines, which need to teach the model how to behave and to adjust its internal parameters. The next 15%, so another 48 million of data, will go to the validation part, which is when the model tunes its hyperparameters and prevents overfitting, which is basically when the model learns the data by heart. And then last 15% would go to the testing part, which is when the model tests the values on an unseen data. And now I'll pass the word to Gabriele, who's going to talk about the model.
So our starting point was this scientific paper, in which they successfully used a bidirectional long short-term memory deep learning model in order to fill the gaps in meteorological data. It was a great starting point. However, it has some limitations. First of all, it just works with one dataset. Second, they analyze only temperature data, so one variable, and then it works at a fixed frequency of 30 minutes. So we made some improvements. The first one is that the majority of our models uses ERA 5 as an auxiliary input. Then we work with multiple frequencies, 60, 30, and 15 minutes. And then we added a new variable, which is wind speed. And it's more difficult to predict than temperature because it has a greater volatility. And so we developed JANO, our family of deep learning models for gap filling. The model, the name model, is a reference to JANO, the double-faced Roman god, who can see both the future and the past. So it's bidirectional, like the first key point of JANO, because it reconstructs the data by seeing both the following and the previous. The second key point is the sequence reconstruction, as the model gives as an output a whole reconstruction of the series, and it's great for multiple gap filling. And the last point is long-term pattern recognition, which is essential for meteorology. And then I'll give the word to Spencer, who will talk about how our models work.
Okay, so we begin the training process with just the raw data recorded from one 24-hour period by one Meteo Trentino station. This particular station records data every 15 minutes, meaning that we have 96 data points in total. It's important to note that because the frequency of observations affects the number of data points we have, each JANO model has to be trained on only one frequency, and then later we have multiple models that can work with various frequencies. Now, we need to create artificial gaps for our model to reconstruct during training. To do so, we take some random permutation of some number of points in our 24-hour period and corrupt them to hide it from the model. We can control the number of points we corrupt, and for our purposes, we decided to corrupt 50% of the values, meaning the model is going to reconstruct half the time series values using the other half of the values. The orange lines represent what points from the Meteo Trentino station our model sees during training. The gaps between these orange lines represent what the model cannot see and what it will be reconstructing. The black dotted line is the true observation from the Meteo Trentino station and represents the ground truth. Our model should fill in the gaps with a time series that is as close to the ground truth as possible. With the input passed to the model, it will begin its reconstruction by scanning from both sides of each gap and then predicting the values that come between them. Here we can see the model's reconstruction and how it compares to the ground truth. Our model also has the unique quality of accepting ERA 5 land data as an input to supplement the uncorrupted values from the Meteo Trentino station. This allows the model to understand the general trend of the weather even if the ERA 5 values are not close to the ground truth values. Now, I'll hand it over to Martina, who will discuss the model's results.
Thank you, Spencer. So, in this graph, we can see... Oh, wait. Yes. Okay. In this graph, we can see that the results of the model training for the temperature variable that doesn't use the ERA 5 interpolations are pretty close to the observed data points. Nonetheless, this can be improved by adding the ERA 5 as a support data input. In these graphs are the results of both temperature and wind speed predictions. As shown, the addition of ERA 5 data makes the time series more accurate, as it tends to follow the general trend of the auxiliary input. You may notice that the wind speed seems to have less accurate results, but that's because, as we've mentioned before, it doesn't follow a pattern, so it's more hard to reconstruct. Now, this table shows the evaluation of the 4 different iterations of our models. It measures their mean absolute error and mean squared error. We can notice some interesting improvements with the addition of ERA 5. In particular, we can see that the mean squared error is reduced by almost 10%. You also can see that the error values of the wind speed are significantly higher than the rest, and that's a result of it being less predictable than the temperature. So, all of this looks very promising. But what does it mean for the future? Having a database without gaps allows us to see the complete climatology of the whole Trentino region. And this is important because having a comprehensive understanding of the long-term weather patterns and climate variability of an area helps us to answer a lot of climatological questions that can have an impact on people's lives. As an example, climate influences agriculture, the choice of crops grown, and the animals that are raised in a region. Tourism and recreation patterns are also shaped by climatic conditions and changes in the seasonality of weather pattern. Water resources availability and utilization all around the world are also linked with climate fluctuations. And despite technological advancements, climate disease relationships are still persisting over time. Now I'll leave you in the hands of Elena and her group to explain the work of Group 2.
Thank you, Martina, and the members in Challenge 1 for the wonderful presentation. My name is Elena, and I'm from the United States. Today, our team will introduce Challenge 2, which is quantitative precipitation estimation from satellite data. This challenge is also proposed by Italian Meteo, which is the Italian National Agency for Meteorology and Climatology. Precipitation is a fundamental component of the Earth's water cycle, which is essential for sustaining ecosystem, agriculture, as well as freshwater resources. To measure or estimate precipitation, we use a variety of methods. For example, the Doppler weather radar, satellite-based passive microwave sensors, as well as the disdrometers. However, despite the many instruments we are using right now, today, accurately measuring global rainfall remains a major challenge. Actually, a recent Nature paper also confirms that precipitation patterns are becoming increasingly variable, irregular, and statistically complex, driven by climate change, natural variability, and land use changes. All of these factors are making estimating precipitation, especially from land, one of the most difficult tasks in meteorology. Amongst the various methods I've mentioned to estimate the precipitation, one of the most effective instruments for measuring it is still weather radar. As a ground-based system, radar directly measures precipitation because it operates closely to where the rainfall occurs. But the problem is the coverage. As mentioned, it is ground-based, so radars only work over land and in regions where there's infrastructure to support them, which leaves large gaps, especially in remote areas and the oceans. On the other hand, satellite provides global coverage, which makes them essential for observing climatic changes at larger scales. But they come with their own limitation, which is that satellites don't directly measure precipitation. Instead, they capture indirect signals, for example, like brightness temperatures. As a result, the current satellite-based rainfall estimates are often biased, unreliable, and uncertain, especially in high-impact or data-scarce regions. With this much information, we wonder, can we build the optimal precipitation estimate? And our team approaches this question by developing a deep learning model that uses satellite data as an input to estimate precipitation fields with the model results that closely approximate ground truth measurements obtained from radar observations over Trentino. Our approach could bring more reliable, faster, and scalable rainfall estimates, especially in regions where the ground measurements are limited or unavailable. With that, let me pass the presentation to Emanuele, who will explain our data.
Where does our data come from? Two are the sources. Satellite data is provided by Severi, which stands for Spinning Enhanced Visible and Infrared Imager, and it's a key instrument on board geostationary weather satellites provided by EUMETSAT, in particular on Meteosat's second generation of satellites. Severi scans a full disk every 15 minutes, and measures reflected and emitted radiance through 11 different channels, 3 of which go from visible to very near infrared wavelengths, while the other 8 go from near-infrared to thermal-infrared wavelengths. Lastly, the satellite has been active for over 20 years, and its spatial resolution is of 3 kilometers per pixel, resulting in coarse images. On the other end, our radar source is Meteo Trentino's radar here in Monte Macayon. It has been collecting high-resolution data every 5 minutes since 1999 and estimates rainfall by measuring the reflectivity of microwave pulses bounced off hydrometers. Stronger reflections typically imply more intense precipitation. However, despite offering high-resolution and high-frequency data, the radar requires calibration and has limited coverage over oceans and mountainous terrain. That's why combining radar and satellite data and enhancing both of them through machine learning can significantly improve rainfall estimates. This GIF shows the overlapping of radar data with data from one of the satellite's channels over time. As you can see, there seems to be a correlation between the two, even if it is to be considered weak. Moreover, satellite data is displayed through 11 channels, further increasing the challenge complexity. However, the existence of a relationship between the data sets the basis for a machine learning approach. The data we used to develop our model comes from the time period from 2014 to 2019, and more specifically, focuses on the data from May to September to reduce the size of the dataset. The preprocessing of data is following these 3 steps. First, to filter data by common time steps, then to merge them into 2 large files, one for satellites and one for radar data, and lastly, to save common time steps to a single file. Furthermore, to ensure proper model evaluation, it has been decided to divide data by season and to rotate the train validation test splits every year to have a more equal data distribution. As you can see, for each season, 2 of the months have been used for training, while the other one has been equally split between test and validation. Next, Anna will delve deeper into our data.
In order to make the processing, we need to make the data compatible in format and resolution. Initially, the satellite has a resolution of 1 or 3 kilometers per pixel, depending on the channel, while the radar has a resolution of 0.5 kilometers per pixel. In practical ways, this means that the radar produces more detailed images, while the satellite is better able to analyze a larger area. For that reason, some aspects of the final image after applying our model can be explained, since it's not possible to obtain images with radar quality while using satellite data as input. Every source of data is limited and noisy in some way. For example, the satellite focuses in high-altitude clouds, since lower-level clouds can be overshadowed, blocking satellite to get data concerning them. On the other hand, the radar faces range issues, being blocked by terrain obstacles and missing data from specific areas. Accordingly, combining these 2 data sources can be useful to expand the amount of information and consequently improve the precipitation estimation, process that will be explained by Samuele in the next part of the presentation.
We implemented an image-to-image system because we take a satellite image as input and return a radar image as output. Which characteristic the model should have to resolve this kind of task? First and foremost, the model should have strong spatial reconstruction capabilities. Weather doesn't happen in isolation, it's all connected. When a storm forms in one area, it's likely to impact the surrounding regions too. This way, the model can just look at individual pixels. It needs to understand the entire spatial structure of the image. Second, the model needs to be capable of multi-data integration. Each channel in satellite data tells us a different information. One shows temperature, one shows humidity, and so on. These aren't separate, they interact. A well-designed model should understand how to combine these signals to create a complete and coherent picture. And finally, we need a robust pattern recognition. The model has to be able to detect complex vision patterns in the satellite images, and more importantly, understand how those visual patterns translate into actual radar signatures or future weather events. For all these reasons, we have used a UNet. UNet is suited for this kind of system because it is a convolutional neural network, which allows it to understand both local and global features in the data. The UNet receives as input a satellite images with its 11 channel that you can see on the left, and returns a radar image as output that you can see on the right. A key characteristic of UNet is its U-shaped architecture, which consists of two main parts. An encoder that gradually reduces the spatial resolution of the input while increasing the number of feature channels to extract high-level information, and the decoder that reconstructs the radar image. But what makes the UNet especially powerful is the use of skip connections between corresponding layers of the encoder and the decoder. Skip connection allows the decoder not to receive only the final output of the encoder, but also intermediate features from earlier stages. These connections allow the model to preserve important features that might otherwise be lost. In fact, thanks to this skip connection, the decoder receives feature maps at multiple resolutions, which provide both high-level context and fine spatial details necessary for precise reconstruction. After developing our model, it was time for the next step that Trento is going to explain you.
So, thank you, Samuele, for explaining which model we're going to use. But now we have to find the best metrics to evaluate it, so to actually understand whether our model is actually behaving correctly or not. So in the end, we decided to use the mean squared error and the mean absolute error. Starting from the mean squared error, or MSE. So the MSE calculates the average of the squared errors of the image that our model does. And what it does is it compares it with the actual radar image and does a comparison pixel by pixel. Since we square the differences, big errors become much bigger, so this metric can actually penalize bigger errors, which is perfect for what we have to do, because in precipitation there can be extreme events, for example, heavy rainfalls, and we kind of do not want our model to miss them. And talking about the mean absolute error, or MAE, it works kind of similarly to MSE, but instead of squaring the errors, it just takes the absolute value of the difference between the predicted and actual values. So basically what it does is it gives us a general idea of our model accuracy. And the reason we use both is that we thought that it was the best strategy, because the MSE helps us with precipitation events, big precipitation events, while the MAE tells us how the model is doing on average. Now that we have the model and the evaluation, we can finally talk about the most important part of our project, our results. And Ludovico is going to cover that.
Okay. Thank you, Renzo, for introducing me. And let's talk about some results. On the left of every couple of images, you can see the ground truth, so the real radar detection. Either on the right, what our model predicts. So, our model is capable of detecting precipitation in both large clouds agglomerate, like in the bottom cases, and in scattered clouds, like in the upper case. As you can see, the results are almost accurate, and the model can correctly identify the precipitation areas, even though they are a little blurred. Let's look at it from behind. This was our input, the satellite that data that we started with. It was a massive collection of files, of images, and starting with this, we were able to develop the prediction model in the bottom, in this case. As you can notice, it's really similar to the ground radar image in its right. So we were happy for what we obtained if you think that these images are just a first result of a few training sessions. Just think how the resolution could be improved in a month of training. So let's talk about our quantitative results. If comparing our research with two different research about referral model estimation models, you can see that our errors are very competitive with the state of the art. I want to point your attention in particular at the second column, because our errors are very similar to the most innovative models that you can find in circulation that was made by AMES. So to improve the model, we can not only do more training session, we can also expanding our data set, either range and in size. And furthermore, the group thought of the possibility of using generative models, such as a diffusion model, which is a kind of deep learning model, neural network mainly used to process and generate images precisely and with high quality. However, it was a realistic option for us due to its complexity and significant computational demands that will require extensive training time and resources beyond the scope of our project. So let's hear about the future application with Renzo again.
So we have our model, we have our results, and we also know how to improve it. But what can we actually do with it? Well, no need to worry, because in fact our unit architecture with the right improvements can actually have the greatest impact in different areas. For example, we have global rainfall estimation. In fact, there are a lot of areas around the world where we don't have radars, we don't have ground stations, so we can now have these kind of measurements. And for example, the sub-Saharan Africa, the oceans. And for this reason, our model could give exact precipitation estimates with the satellites alone. Also, we have the disaster preparedness and response. In fact, by detecting heavy rainfall zones quickly and accurately, our model can support flood early warning systems, helping the rescue teams to move faster. Lastly, there is the precision agriculture. This is important, for example, for the agriculture-dependent economies. Well, because the timely rainfall predictions would enable better crop planning and irrigation management. Thank you. I'm now going to leave the rest to the group number 3 and to present their challenge.
Hello everyone, I'm Arij El-Girni from Saudi Arabia, and today I'll be presenting to you, alongside my teammates, the third challenge. Now, accurate weather prediction has always been a significant challenge, one that we aim to solve via subseasonal forecasting. What is subseasonal forecasting, you may ask? It is essentially that very tricky period in between medium-range forecasting and seasonal forecasting. Now, medium-range forecasting, while very challenging, already has existing technologies that allow for its successful forecasting. And the same goes for seasonal forecasting. While it's also a very hard challenge, it follows a more predictable pattern in the sense that winter can be colder than summer and so on. However, this tricky period in between 2 to 4 weeks still has a significant research gap, one that we aim to fill within this challenge. Why are we trying to fill it anyway? Because of its importance and significance across various sectors. From the agricultural sector, in which certain companies, farmers, and producers will need to understand the upcoming weather conditions so that they can prepare for extreme weather events, droughts, and protect the crops and produce. Also, the health sector is very important in the sense that hospitals and agencies can prepare for disease-related conditions that are affected by climatic changes. And so having weather predictions for that will be very helpful in reducing the spread of these diseases. Also, additionally, we've got the energy sector, in which understanding upcoming weather conditions will allow us to prepare in sense of, for example, electricity, whether we're going to be needing to cool or heat up these systems depending on the weather conditions, in renewable energy, solar panels, and much more. Of course, the importance of subseasonal forecasting is not limited to these sectors, but only highlighted through them. And to further emphasize its importance, we've got the European Center for Medium Weather Forecasting with a global challenge that they've hosted for scientists, students, and individuals worldwide to try and attempt to solve this issue, highlighting its global importance and the urgency for subseasonal forecasting. And so with that, I'll leave it to Filippo to guide you through our project and its previous works.
The first step we took was the literature review about some papers about the machine learning, as it's the most recent way to approach the subseasonal forecasting. We took inspiration from these works to start our project, and we set one goal that was forecasting temperature anomalies. What are temperature anomalies? Temperature anomalies are the difference between temperature observed in a certain day and the long-term average temperature we get from a data set from 1980 to 2010. The graphic you see is the temperature anomaly of Europe in 2022, where the warmest color represents where the anomaly is higher. We use temperature anomalies for two main reasons. The first one is to bypass the regular seasonal cycle, as we all know that that summer is hot and winter is cold, and to highlight the climate trends and the extreme events. In order to predict temperature anomalies, we use the geopotential height at 500 hectopascal, as Arianna is going to explain to us.
The geopotential height is the height at which we can find 500 hectopascal of pressure in the atmosphere. It is important because it helps us to capture a large scale of weather patterns, and it helps us to understand and predict the atmospheric behavior, as that we can reconstruct the temperature anomalies. This is because these patterns are important because there is a complex but recurring relationship between temperature anomalies and geopotential high patterns. These patterns are recurring atmospheric structures that correspond to a surface condition. They are associated with the well-known climate phenomenon, like ENSO, that is found in South America, and NAO, that is found in Europe. For example, as we can see in the slide, the NAO influence the temperature anomalies in Europe. Those patterns are useful for our goal. So we extract this pattern by using the EOA analysis, that is an empirical orthogonal function. And once that we had extract the patterns, the most relevant patterns, we transform them into indices that are represented in a time series. By combining these indices, we can reconstruct the temperature anomalies. These indices are the numerical representation of the similarity between the patterns and our current situation. Higher is the value of the pattern, stronger is the similarity. For example, if we consider the 25th of July 2007, we can see that in the indices that represent the NAO, the North Atlantic Oscillation, there is a high value. That is mean that in this day, the weather was more similar to these indices. On the contrary, the indexes that represent the ACA and the EA are lower. So our group focused on compute these most relevant patterns and transform them into indices, and with an artificial intelligence model forecast these indices. Now, Elisa will talk about our workflow and how we achieved this challenge.
In order to achieve our challenge, among the various datasets, we chose ERA5 because it contains the best data for our project. This dataset provides us all the daily temperature at 2 meter high and also the daily geopotential high all over the world and over the past 84 years, from the 1940 to 2024. So, when we had our dataset, we started wondering about the challenge itself. Firstly, we tried to do an EOF analysis all over the world, but as you can see, there was a problem, because in the middle of this picture, there was a lot of white. It means that we were not able to reconstruct the weather condition in areas such as South America, Africa, and also Asia. In order to overcome this problem, we divided the Earth in 9 different regions so that we can focus on each region once per time. Then we apply again the EOF analysis to each region, and we found 36 different patterns. And as you can see, we succeeded in find something meaningful also in the equatorial line. In this way, we found 36 patterns, but not all of them were useful for our challenge, so we had to select between them. How did we select the most meaningful patterns? Firstly, we found the correlation between each pattern and the temperature, because our focus was on the temperature in this challenge. So, as you can see, we have 2 examples of different patterns. The first one is really connected with the temperature, as the colors in the second picture are spread all over the world. While in the second picture, instead, we have nothing in the second picture, which means that it has a really weak correlation with the temperature. So in this specific case, we decided to take the first pattern, but not the second. So we did this work for all our patterns, and we found 17 most relevant. After finding these indexes, these patterns, we had to extract the indexes that are the similarity between the pattern and the specific weather condition that we have in a determined region of the Earth. So now Arich is going to talk about the model that we used to do it.
Okay, so now that we have a great theoretical background of the study, let us step into our actual machine learning forecasting model. Before starting with a model, we had certain requirements set so that we can choose an architecture that would be successful for the purposes of our challenge. The two main requirements were that the machine learning model can find nonlinear relations whilst also working in a constrained data environment, one that is 31,000 data points in total. Of course, to achieve or select a model that can achieve our challenges, a certain pros and cons list was made. One that focused on simpler models like linear models, such as linear regression ones, which showed that they have the certain pro that is they can train with fewer data points. However, a certain negative is apparent, which is that they can only find linear relations, something that would not work for the purposes of our challenge. Now, on the opposite end, we've got more complex generative models, such as transformers or diffusions. These models have the counter effects, or the opposite of the simpler ones, in the sense that they can find complex, nonlinear relations while also needing millions of data points, something we lack in the context of our challenge. However, we're lucky to say that there's a sweet middle ground in between, one that takes the best of both worlds: long short-term memory, LSTM models. They can be trained with fewer data points, and they can also identify complex, nonlinear patterns, making them the ideal model for the purposes of our challenge, which is subseasonal forecasting. And so, I'll leave it to Thomas to walk you through the model setup, the training, and validation.
So in order to create a model that would be able to effectively forecast indices for the future, we had to first divide our data set into 3 different sets. First of all, we have the training, and then we have the validation and the testing. And in order for the model to be able to accurately understand the complex patterns we're giving it, we need to devote a significant portion, in our case 70% of the data, to training, while we gave 15% to validation and 15% to testing to allow the model to evaluate its performance. So we set up 2 different model forecasts, where the first one would be more of a mid-range baseline for our model, taking 30 days of input and attempting to forecast the next 10 days of indices, while our second setup would take 42 days of input and attempt to predict 28 days or 4 weeks into the future of these indices to truly attempt to fulfill the subseasonal forecast. So let's examine some of our results. Here we have a sample 10-day forecast using 4 of the 17 indices in order for visualization purposes and to reduce cluttering. On the left, we have the input data, and separated by vertical bars where it transitions to an output. The dotted line represents the predicted value by our model, and the solid line represents the ground truth. As we can see, for this short-term model, we have very strong data and promising data in the fact that 10 days into the future, we can still, for certain patterns, model very closely what they should be. For example, the red, the green, the yellow, they're all pretty accurate. As we extend this forecast to 4 weeks, we begin to see a little breakdown in the accuracy. This is due to various factors such as the natural unpredictability of weather weeks into the future, but also the limited data constraints that were mentioned earlier. However, certain patterns such as the yellow and the green, we can still see there is high correlation even 4 weeks into the future, which is very promising for us as a baseline for future research. And now I'll leave it to Giulio to talk about our results for each index.
Thanks, Thomas. Now we are looking at a chart that shows the indices predicted by our model using a mean squared error. This chart is very useful because it helps us understand which indices the model was able to predict best. In this case, the best prediction is for index number 13. This is a very important result because index 14 is related to El Niño. El Niño is an important climate pattern located in the central part of the Pacific Ocean, close to the equator. Its effects influence all the globe. It has a strong correlation with temperature, especially at the equator. This graph compares the real and predicted El Niño temperature, we can see the model is a good in forecasting Niño, up to 10 days, but it underestimates the Niño temperature on a long time scale. Understanding of El Niño flow is really important to understand climate science, so the possibility offered by our model to predict El Niño's flow is a strong result for us. To sum this up, we achieved the following points with success. Identify the optimal indices and pattern for our project, achieve the competitive performance forecasting for 10 days. The work for the future to improve this challenge are using a more advanced machine learning model, using other weather variables, not only geopotential height and temperature, but use precipitation, humidity, and wind. Thank you, everybody, for the attention. I leave it to Arij to discuss overall conclusion.
So now we've reached the conclusion of this beautiful presentation, and I would like to take a moment to take you back to our journey of this 3 weeks. It has been a journey of networking, learning by doing, and teamwork. We were able to connect with and learn from experts in the field, be it in climate science or in weather data, as well as technical ones. And we were also able to dive headfirst into the world of research through the challenges we were assigned, allowing us to learn and experiment through trial and error and experience what it's like to be a real scientist. And within those challenges, we were able to develop certain team working skills that allowed us to communicate better. And whilst also working together as a group, we were able to delegate certain tasks to each person so that we can assign it based on strengths and work in a productive, proactive environment. And so, what have we learned in these 3 weeks? Technical skills in data science, machine learning, Python, algorithms, as well as soft skills that include design thinking, time management, as well as overall problem solving and interpersonal communication. But I would say that the biggest takeaway from the program is definitely adopting a research and innovation mindset. We learn to ask the questions, to say why and how, and take a step and attempt to solve it. Whether it turns into a success or not, we would have left a fingerprint in the beautiful world we call science. And so, our contribution to the community throughout these challenges were global, national, and local. On a local scale, we were able to achieve successful data reconstruction in the Alpine region, while on a national scale, we focused on precipitation estimation, and on a global scale, we focused on subseasonal forecasting. But I would say that there's one thing that merges all these 3 themes, which is innovation. We learn to become better innovators throughout working in these challenges, and we learn to think outside of the box and try to attempt different solutions. And so, that would not have been possible without the support of our scientific partners. Big thanks to Italia Meteo, Meteo Network, and Meteo Trentino, who provided us with informative sessions, global support from successful mentors, and overall tools to allow us to learn more about data science and climatology. And the program itself would not be possible without the collaboration and partnerships of several institutions, not limited to, but including Artigianelli, Arcivescovile, Autonoma, Provincia Autonoma di Trento, Regeneron ISEF, Collegio Dante Alighieri, and Science Technology Society. So, that we've come to the end, I'd like to leave you with one question. Do you see what happens when you give young minds real tools, real data, and real purpose? You get WebValley. Thank you so much for listening, and please feel free to ask any questions.
Thank you very much, everybody. I invite Martina, Roberto, and Andrea on the stage just to have a comments and some questions to our students. Thank you very much. Please, you don't have... Martina, Roberto. Oh,
Yes.
Thanks.
Okay, let's give them maybe...
Okay, thank you very much.
In the meantime, I think we can say thank you. I'll take the freedom to talk for the three of us to say thank you for having us here today. And thank you, all of you, for the impressive work you have done and for the amazing presentation you gave us today. Vicino alla bocca. Okay. Hope everyone here heard me. Yes. Okay. So again, thank you. And I can maybe start with the first group. And yeah, so do you think the model can be improved by giving it as input not just the target variable, but also other correlated variables?
May I
Yeah.
answer? Okay, so surely, I am Gabriele. I am part of Group 1, and I have developed the model. So, the model can be further improved by adding additional variables, such as longitude, latitude, and height, because if you have lots of data, you can associate the height and those other variables in order to add them up and have a more precise prediction, because you can further improve the precision by correlating at, for example, which height is the station, because, for example, the ones in the mountains have a lower temperature. So our model can't do that because it is specific to one station. But for example, more difficult and complex models, such as transformers, have the capacity of doing that.
Okay, thank you. Do you have a question? Group 1?
Hi, thank you for the top-notch presentation. It was really interesting. And I would like to ask, if you focused on time and wind intensity, temperature and wind intensity, what if you also try, I mean, I understand it's understandable choices given the huge amount of data you are facing, so it's totally understandable, but what if including more data would help you in the sense that maybe wind direction and the precipitation might be good predictors for actually filling the gaps on the other data, like, have you considered that? Or even maybe if one station is not completely off, but can just measure temperature, but not wind, for example, maybe that could help also.
Yeah. Actually, we used a lot of stations, and they are very different from each other. So maybe some stations only measure temperature, other measure only precipitation or wind direction. And we used only temperature and wind speed because of the time. We worked on this project for 2 weeks, and we had the time to train the model only for these 2 variables, but if you can create the data sets with the other variables and train the model, it will work even with other parameters.
Okay. Thank you.
You're welcome.
I am very old, and so comparing to you. But when we study to fill the data missing, we use the correlation between nearby stations. So I ask you, did you try to use the nearby station instead era 40 data to fill the gap?
Actually, no, because we used year 5 as the ground truth, so we don't really need like the data from the near station, because they were really precise, even if only year 5. Maybe there's something that we can improve in this model, and it will work better.
Yeah, I have another question. When you were talking, I guess, about the spatial resolution or temporary resolution, you were talking about the way you match them, the different data set. You talk about multiplying. Am I correct?
So yeah, just because the model needs equal number of values, both from method Trentino and from ERA 5. So for example, if we have a frequency for method Trentino every 15 minutes, we have from midnight to 1 a.m. We have midnight, midnight 15, midnight 30, midnight 45, 1 a.m. Instead for ERA 5, which has an hourly frequency, we have just 2 values. So we basically took the midnight, for example, the midnight value, and gave it the same, but used the same value but with a different timestamp. So it would have the same value from midnight to midnight 45, and then at 1 a.m. it would change. So we could have matching number of inputs between both the data sets.
Okay, I see. Okay, yeah. Anything else on group 1 that you want to ask? No, okay. So maybe group number 2?
Okay. We could switch to the second group, the satellite to radar, learning models. And I was wondering, it started from 11 bandwidth from the radar images, and did you check whether some bandwidth were constantly more informative than others, maybe also related on the surface? Like the ocean or the mountains, maybe some bandwidth were constantly more informative. Like
we of the 11 channels that we had, in the end we decided only to use 8 of them, because of the 11, 2 of them were visible channels, and 1 of them was very near infrared, which means that it was basically visible too. So during the night, those measurements were not accurate. So we decided to exclude them for the model evaluation, for the model training.
Okay, but I was wondering, maybe, since you were considering both the ocean, mountains, and land, maybe some of those channels, for example, on the ocean might be constantly like non-informative. I was just wondering if you could like consider that in order to decrease the amount of data that you have to analyze like constantly, so to make them more manageable the computation.
We did not incur in this problem because we only worked on the Trentino zone. So, for example, the ocean was not
an option.
It was not an option, so we did not incur into that problem.
Okay.
Just to add on to that, I think that's a very good angle that we could put in the future, because we also mentioned that as part of the application, our goal is to expand the model and then use it in different locations. So that's definitely part of the consideration.
Exactly.
Thank you.
Okay, thank you.
Then I have a question. Like, can your model be applied to other regions?
Yeah, we think so. We think so. Maybe we could train with the data from the region, but also I think the model that we have trained on Trentino is really good and perform really well, I think, for the time that we had.
Maybe since it's trained on a zone where there are, for example, mountains, and it cannot measure
the radar cannot estimate precipitation beyond the mountains. And what our model does is create an image similar to the radar one. Maybe, for example, if taking into consideration a zone without any mountains or no structures, it could give some problems because there are some connections between the clouds that the satellite gives, the presence of clouds that the satellite gives, and zones where it would rain, but the radar does not catch that in this zone because there are mountains. That could make the model less accurate when there are no terrain structures.
So the performance will change?
Yes, but not that much, in my opinion.
Okay.
No, I'm good.
No, that's good.
That's good.
You use the data of our radar, correct? But our radar is at almost 2,000 meters above the sea level, and so it measures what if it is raining at about 2,000 meters or more. So probably there is some times that you see the clouds from the satellite, but you don't see rain because the rain, especially in winter, is lower. Do you think that you can improve the model using also the rain gauge from the weather data station?
Yes, probably we could, but to partially tackle this problem, our input data is only from the months from May to September to partially tackle this problem of the lower precipitation.
Then we go to group 3, I guess. Yeah.
I was wondering if you could explain a bit more how you derive the indices from the geopotential height.
We take our data, the geopotential height data, and from them we extract the pattern by using the UF analysis. So by the indices, the patterns were transformed into indices, and they are the representation between the similarity from our patterns and our current situation, so how the weather was in this day. So they are a numerical representation, and we use the UF analysis.
Okay, but I was wondering how you match the index with, for example, El Niño. Like, is it straightforward, or
Every index has a correlation with the pattern. So, for example, we have an index for El Niño, we have an index for the NAO. So, if we see that the index for El Niño, for example, is very high, it means that this weather patterns is really similar to
if
the El
it
Niño.
correlates, then you
Yes.
can tell that they move like accordingly. So
Yeah.
that's okay. Thank you.
I have first like a general question. So while introducing the challenge, you explained, like, you said that subseasonal forecasting is a tricky one. Do you know why is that tricky?
Essentially because, as far as my understanding goes, for medium range weather data forecasting, in which it's about 10 days to like weeks, it's easier in terms of the fact that cloud formations and other like geographic indicators can help us predict the weather, and that's how like weather forecasting and weather apps can work technically. And as for seasonal forecasting, there are certain patterns that are expected, which is January is almost always going to be colder than July, and so it's easier to predict how seasons differ. However, when it comes to subseasonal forecasting, which is not close enough that you can just rely on cloud formations and geographical regions, but not far enough that there's a specific pattern repeated. That's where the tricky part comes in, and that's why there's a research gap that scientists are currently trying to fill.
It's not my field, but we know that a seasonal forecast has a skill in the region that are affected from El Nino. It's basically you have a skill in that region where the water circulation changes during El Nino or La Nina. In the other place, we are not able to forecast with the usual model. If you go on the web, you can find the seasonal forecast, but in Europe, the skill is very low. Do you think that with AI models, you can reach some results, some skill, or it is impossible to forecast the seasonal change?
So I think it all comes down to kind of the data we were working with. What we had was essentially one data point every day for the anomalies. And in terms of how time progresses, one day is not very specific in order for us to really get a grasp of how the weather was changing throughout that day. So if we have more data, I think it would be a lot easier for us to essentially look into these different regions and be able to do a subseasonal forecast with more accuracy.
Thank you.
And one other question. Did you forecast each index independently, or did you use a multivariate forecasting approach?
They were all evaluated independently. So the graph that I showed was just an example of the first 4 we had in the set, but each of them could have been graphed on there, and you could see the progression of them. So they have little relation with each other because they're all forecasted for specific areas of the globe. Certain ones are repeats of the same area, but with a different pattern. So essentially, they're all independent of each other, and yeah, there's not much of a connection between them.
One more question for group 1 and 3. Group 1 introduced us with Jano, which has a very cool feature of being bidirectional. So, but it's also a sort of a drawback in the sense that it would be maybe cool to be able to impute data in real time. I mean, data is missing, and you want to fill it in like in real time while it's missing. Maybe you want to have some, I don't know, precise and local prediction in that place, but you have no data. What if you try to use the same system Group 3 introduced and try to make a direct prediction? Have you tried that? Have you thought about it?
We didn't try it because I thought about something related to the Group 3, so I told the leader of the Group 3 that maybe the data reconstruction can help their project. But in 2 weeks, it was a little bit impossible to do. But maybe in the next days, in the next times, if someone wants to work on our projects, maybe he can find a solution and combine these 2 projects together.
That's totally fair.
So I would also add that these 2 challenges are very linked with each other, because without the complete history data, you can't do forecasting. So our model is specialized on filling the gaps. Yes, the bidirectional model could be adjusted to work only with previous data in order to do a prediction, but obviously it wouldn't be as optimized as we developed it for filling the gaps because the objective was different. However, yes, it could work, and I'm really happy that
these two challenges are very linked with each other because you are basically having a small taste of how scientific researches work. Because I do my part, I give the result, and then the others can improve it and use it for other things as subseasonal and forecasting.
That's great. Thank you.
And maybe just to conclude, do you have other questions? No? Did you think about what at the beginning of week 2, I met with you and we discussed like applying for the ACMWF call. What did you think about that?
Yes, we're still currently trying to better our results in the sense of successfully fully achieving subseasonal forecasting, but we've created a team name, we've written a research manuscript, although still a draft, and yeah, we'll hopefully submit to that.
Oh, that's great.
Thank you.
Okay. Thank you.
Thank you very much. I don't know if someone from this side has something to say or add. Okay. Otherwise, I think that you have done really good work. And now it's time for you to enjoy also the evening together. Finally, without slides, without code, without programming. Okay, maybe, we take time to have some pictures together to say goodbye to you and to all the tutors that stayed with you these 3 weeks. So please do not run away really fast, but stay a bit with us here in the garden. And thank you, Martina, Roberto, and Andrea for joining us today, but also in these 3 weeks. It was really nice to having you with us. And all the people here, relatives, teacher, and friends that came and stayed with us this afternoon. So thank you very much. It was really nice.